After long and tedious execution of this is where we ended up. So remember, we started from here, then we did this line, and then we did this line, and then next we did this line, and we needed this line, and ultimately we did this one, and ultimately finished here. This way, how many operations did we really have to compute? We will see in a bit, but ultimately we reached to this point. And now we will roll back. We will roll back using the backward arrows. So I will go this way, and then this way, then this way, and then this way, and then this way, and this way, and then this way, and then this way, and then this way. And now I will read how I match my sequences. Let's start from here. Remember, this was the first, this was the second sequence. So I start reading A from the first sequence and A from the second sequence. Now I took second A from the first sequence, didn't move in the second sequence, so I matched with space. I exhausted the second A from the first sequence. Then I matched G and G. And currently I'm here. Now I'm matching C and T. Once I matched C and T, I basically did this. Now I'm matching again C and C. And then T and T. Now I'm matching A and A. Now in the next step, I'm not taking anything from the first sequence. I'm staying here, so this is space from the first sequence. But I'm inserting C from the second sequence, and ultimately I'm taking C from the first sequence and C from the second sequence. So according to all of this, assuming I did not make major mistakes, this would be the optimally matched first sequence with the second sequence, and here we read what would be the cost of this. Again, if you don't mind, you can repeat all of this by yourself and see whether or not I made some mistake. What is the complexity of the algorithm? Remember what we are doing. We went here. For each such cell, I need to basically calculate 3 possible costs and choose the smallest one. And I need to repeat that calculation for each of the elements in these cells. How many of the elements? Here is the size of sequence 1, and here would be the size of sequence 2. So the time complexity is theta of the size of sequence 1 times size of sequence 2. Assuming these two sizes are equal, n, we will get that the time complexity is theta of n squared, which sounds familiar because if you could remember, the time complexity for Viterbi algorithm was n squared times t. Space complexity we essentially need to maintain 2 kinds of things. We need to maintain the current costs, which are the numbers here, and we need to maintain the arrows. Arrows mean actually from which cell I reach to a given cell. So this arrow means that to this cell I reach from this cell. And as you could guess, basically to calculate the weights we just need the weights in the previous row and column. So the space for the weights is not critical, but the space for arrows is critical, and ultimately we can get that the space complexity is also theta of the size of sequence 1 times sequence 2, and if the sizes of sequences are equal, the space complexity is also theta of n squared. So we've shown one very practical algorithm, which is, or either this algorithm or some variants are really used in bioinformatics for matching sequences. This completes my long lecture on dynamic programming. Thank you very much and have a nice day.